Hi everyone, just wanted to get back with you now to finish up this lecture on the second law from Kepler's planetary laws. And again, what we did so far is we found that you have to choose a time, draw lines from the origin, which is where the first focus is that the moon is centered on, and you do that for an area over here, area over there, count the squares, and then do a comparison. But what we see here obviously is that when you're closer to the moon, you go faster because that's a farther distance for a half an hour versus the distance farther away from the moon. So that's another rule you get from this. That first off, remember what we have is that orbiting bodies change speed in their orbit, but they do so in a set way. Closer, they move faster, meaning closer to what they're orbiting. Farther, they move definitely slower. And so that's the interesting thing, but the more important question maybe is, even though this is important, is why does it move this way? What is the underlying reason that things could change their speed and change it in such a manner that you go faster when you're close and slower when you're far? And so, well, we just draw this ellipse once more. So, getting good at this, aren't I? Well, maybe. And so we have the focus that the moon is centered on. We have the other focus, which is just out in space. We just need to have two foci for every ellipse because remember, when we did the first law, we had to have two foci to be able to find the lengths to prove that the orbit was elliptical, and go back to the original lecturettes that discussed that if you're questioning. More caffeine, guys. I think I'm living on it. I just had 2 bags of coffee delivered. I'm doing all right. So, what we have here then is the idea of something that seems to give a rule in regards to this way of how things move. So if this is the satellite, I can draw a line out from the center of the moon. By the way, this is the major focus. Let's get some major axis right here. We call that line a radius. So R is known as the radius. And really what we're referring to is the length of that line in terms of the units of meters. And just to remind you, a meter stick looks like this. So this is 1 full meter, which is the set unit we use for length in the sciences. And then we use an arrow that indicates the direction that it's moving with, and V is the speed. V is the speed that it is moving with. So it's the speed of the satellite. In other words, if I'm moving around and I can have an arrow point in the direction that I'm moving in, then the direction of the arrow is the direction of motion, and the length of the arrow would be related to the speed. So a small arrow would be a slow speed. A long arrow would be a fast speed. So we use that arrow as a means of denoting something called velocity or speed in this case. And then we have the mass of the object. So m is the mass of the object. And of course, in this case, is the mass of the satellite that's actually orbiting the moon. And the mass, remember, is just a measure of how much mass, or excuse me, of matter that an object's made from. The unit of this is the kilogram, as we've learned in class. This is in meters per second. And there's one other quantity there. That is the angle between the distance r and the speed v. And we'll call that the Greek letter theta. So that's the Greek letter theta. So theta is the angle between R and V. Now, one thing you know is as the satellite is moving around, two things happen. Really, three things happen. One is the length R is continuously changing, the speed V is always changing, and the angle between them is always changing. The mass remains the same. Now, you know, it's funny. One of the things that physics does is it studies the motion of objects. And as we do these studies, it's all mathematical. And as we try to analyze how things move using mathematics and the laws of physics, one thing that crops up basically are the same thing, mathematical expressions that seem to come often in these calculations. So if I'm studying how something's orbiting, or if something's moving in a straight line or whatever, that as we do that analysis, in that mathematical reasoning, certain terms seem to always show up. And in fact, they show up so often that it becomes really important to study those things themselves besides the actual motion. And one thing that seems to have showed up all the time is something called angular momentum. So L, capital L, is known as angular momentum. And angular momentum is something that is a measure of, gives a measure of the motion of an object that's moving in some type of curve, like this satellite's moving in the curve of the ellipse. And we always find that. And it turns out that L, angular momentum, is equal to the mass times the speed times the length r, and then something that you're not required to know for this particular class. And so we're going to have to find a way to get rid of it because you don't need to know this. Something called sine theta. It's just a trigonometric term related to the angle between r and v. But you don't want to deal with that. Now that's what angular momentum is equal to. And it's just found often in calculations studying the motion of things moving in a curve. Now, you're not going to need to know that whole thing because you don't need to know sine theta. That's not required in this class. So there's going to be a way to get rid of this. Now, one thing we know is that the pivot, what this is pivoting around, let me be more specific. What that satellite is pivoting around is the center of the moon at that focus. So right there is the pivot. And what's really astounding is that we can relate the motion of that satellite, how it moves in its orbit around the moon, so that when it's close it goes faster, when it's farther away it goes slower, to that motion of a skater. So imagine a skater and their arms are out. I got both arms out and I want to pivot around myself. Let me kind of back up and maybe I can do it here. So if I've got my arms out like a skater and I want to pivot around, what happens if I raise my hands up? Now when I pivot slowly, it's because my arms are out. So when my arms are out, I pivot or spin slowly. If I raise my hands up as I'm spinning, I'll spin faster. What's the pivot? It's really a line right through the center of my body. So when the mass that makes me up is farther away, it's kind of like the satellite being farther away, I go slow, like the satellite goes slow. And when I put my arms up in the air, I'll pivot faster. And that's like being over here. And so the same type of relationship of a skater spinning on themselves on the skate rink is the very same thing that's happening with a satellite because of something called angular momentum. The pivot is the center of the moon. And so that's what we have to understand. Now what we want to do is get rid of that sine theta. And it turns out there's a way to do so. It turns out that in this sine theta, the sine of 90 degrees, you don't have to remember this, I will not ask you this, is equal to 1. So if I can find two places where the angle between R and V is 90 degrees, and I can do that, then what happens, sine theta just becomes 1, and so it simplifies then simply to mass times speed times the distance R. So where is that? So the places for that is on the ends of the major axis here. I'll call that point 1. And the ends of the major axis over here, I'll call that point 2. And so let's look at 1 first. For 1, this is my distance R1. And remember, it's going to be going very, very fast at this point because it's as close to the moon as possible. So here's my arrow, and when I hit to the end, the arrow of motion is straight up and down, and it's going to be long. So this is, at right angles, my speed V1. Now then it moves around. The distance R is getting bigger, but the speed is getting smaller. And so out here, what I find is that at point 2, here is my R2, and my speed at this point is V2. So it's coming around, moving down at that point. And again, this is at 90 degrees, and the other angle is also 90 degrees. So we can get rid of that sine theta. Let me go ahead and erase this down here. Since you have this, you can always go back, and you should have this in your notes. You should be writing this stuff out and summarizing what these lectures are in your notes so that you're forced to pay attention to it, and you're forced to actually rewrite this so you have it and understand this. So what we are given in this is something called the conservation of angular momentum, and we're going to find out it's because of the conservation of angular momentum that the satellite moves the way it does. So the conservation of angular momentum simply means that L is a constant, where L is angular momentum. It never varies. So if I call this point 3, that's point 1, point 2, point 3, what this says is that the angular momentum at point 1 equals the angular momentum at point 2, which also equals, more generally, the angular momentum when theta is not 90 degrees at point 3. So I'm just going to focus here. We have the mass times the speed at point 1 times the distance at point 1 equals the mass times the speed of at point 2 times the distance at point 2. Now the mass stays the same, so we can just ignore that. It doesn't play a role. But see, that equal sign means a lot. Because see, since the mass doesn't matter, I can just get rid of it in this consideration discussion. When R is very small compared to R2, R1 here is very small compared to R2, I'm going to put a down arrow indicating it's small. I'll put an up arrow for R2, meaning that's big. If that's going to be big, then that has to be small in order for that to equal this. If that's small, this must be big in order, so this is the case. So if this is 5 times 2, this must be 2 times 5, so that they would equal, as an example, just pulling some numbers out. So what does this say? Because angular momentum is always the same value no matter what, it means that when R gets small or big, then V must change. So in this case, when R is small, V must be big. When R is big, V must be small. And so that explains why the motion changes in the orbit and why it changes the way it does move that way. So if I look at the book, just making certain we kind of walk through this. So this is basically looking on page 94. You see the same drawing as this. Asks what the conservation of angular momentum is. It means the angular momentum never changes, always has the same value no matter where the satellite is at. Asks for you to define all the terms in that equation, which we have on this video. If you go to table 6, look at your data and just say the way to answer this for L1 or L2, referring to the figure on page 94, you see again 0.1 and 0.2. Just tell me, is the radius R, is that big or small? Tell me if the velocity is big or small for 1 or 2. And so there's no calculation of that, just whether or not something's small or big. So don't make that hard. And then finally, answer those questions 1, 2, and 3 at the bottom, page 95, going back and saying where does it move the fastest, where does it move the slowest, and so forth. And again, just repeat again what is conservation of angular momentum. Sometimes repetition aids learning. So, what does this leave us to do? It leaves us to do the final law, which is Kepler's third law. And that will be the purpose of the final lecturette for experiment 7. And I plan to post that today, at the latest tomorrow. And so you'll have everything to do this lab and this experiment number 7 by the end of this weekend. But you need time to do this. So I'm going to give you out until a week from next coming Wednesday to finish this up. And then I'll have you post your results via an email, like we did lab number 6. And so that's, I think, all there is for this particular one. I hope you're doing well. Keep looking and working. Don't get behind. Be regimented in your work. Know where you are. You're in college. You're doing the work that you're supposed to do so that you have a future ahead for yourself. And use this as a time to keep focused in the work that you're doing. I am watching for emails. I'm watching for all your needs. So let's get this done. Take care, guys. Bye-bye.